Okay, in this section we're going to look at solving exponential and logarithmic equations. So the first thing we'll look at are solving exponential, and there are two types of exponential equations and two types of logarithmic equations. That we'll be actually look at solving. So under exponential equations, we're going to look at things that where the bases can be expressed as the same base, and then we'll look at things where the bases cannot be expressed as the same base. And so I'll just give you a quick example of this. So for example, 2 to the x equals 2 to the fifth power. And in this case, what would x have to be? It would have to be 5. We didn't really divide out anything. We just acknowledged that in order for the left side to equal the right side, they have to match. Or we might see something like this, where 3 to the x equals 27. And you're thinking, well, what does that have to do with anything? Well, I can rewrite 27 as 3 cubed. So I can re-express, I apologize for the handwriting here, I can re-express this as 3 to the x equals 3 cubed, in which case x is clearly 3. Okay, so now what happened here? What I physically did in both examples is I changed both expressions to the same base, and then I set the exponents equal to each other and solve. Now, when the bases don't match, so let me kind of give you an example of this. We have 3 to the x equals 26. Okay, so there's no power of x that'll ever get that to work. Or I might have 2 to the x plus 1 equals 15. Again, I can't re-express 15 in terms of 2, so we've got to come up with a new rule to do that. So what we're going to do is we're going to isolate the base with the variable. Isolate the base with the variable, sorry. The base with variable. And then we're going to take the natural log of both sides. And this will cause, or this allows us to take the variable with the exponent to move the coefficient of the expression, which is called the power rule. So when we take the ln, that allows us to now use our ln rules, and then we're going to solve for x. Okay, so our first type is to solve an exponential equation with a common base. So we kind of got a sense of this already. This is where we can rewrite it in terms of the same number to some different exponent. So once we get it in that form where the bases match and I just have two different exponents, then we're going to set up an equation where we set the exponents equal to each other. Okay, so let's kind of look at some different illustrations of this. So 4 to the x equals 16. So first thing I have to come up with is what's the common base? What number can I rewrite in terms of what exponent? And I can think of a couple of ways that I could rewrite 4, so 2 to squared, for example. And I can also think about 2 in that sense for 16, but 4 and 16, 16 is just 4 squared. So I can rewrite this as 4 to the x equals 4 squared, in which case, what does x equal? X is 2. In the next example then, now I have a base of 2 and 16. So now I do want to rewrite that in terms of 2. So 16 is actually 2 to the 4th. And now I want to set the exponents equal. So 3x minus 8 equals 4. And then I want to just do my algebra solving skills. So I want to add 8 to both sides. Gives us 3x equals 12 Then I want to divide by 3, and I get x equals 4. Okay. Next up is 27 and 9. So we need to think of a common base that works. Now, 9 is 3 times 9, so 27 is 3 times 9, but I need some number to some power. So I don't think 9 is going to work. I don't think we need to focus on 9, so I need another number that I could rewrite 9 in terms of, and that would be 3 squared. Consequently, 27 is 3 cubed. So I can rewrite this as 3 cubed raised to the x plus 3 power equals 3 squared raised to the x minus 1. And then we have a rule that says an exponent to an exponent is going to multiply that out. Well, now what? Now I'm going to set the exponents equal to each other and solve. So if I distribute the x in, I get 3x plus 9 equals 2x minus 2. Let's subtract off a 2x, and let's subtract off a 9. Okay, and so what does that give us? That gives us x equals negative 11. Okay, so next up is this 9 1/3, and we have to sort of think about, well, what exponent rule can we apply now? And I see the 9 and I see the 3, and I can clearly rewrite 9 as 3 squared, so that's fine. But what about that 1/3? Well, remember, there's a rule about negative exponents. It implies that we're dealing with denominators. So 1/3 is really 3 to the negative 1. And so now I can just set the exponents equal. So I get 2x on the left equals negative 1. And this time when we solve, we get x is negative a half. And we can even extend that trick a little bit further, because dealing with square roots, let's see, that 9 is still 3 squared. And that's really 3 to the 1/2 power. So if I continue with my exponent rules, let's see, that'd be 2 times x is 3 to the negative 1/2. So now I got the basis to match, and I'll just worry about the exponents then. In this case, dividing by 2, I'm going to multiply by a half, which is the same as dividing by 2. Now on the left, notice the 1/2 and the 2 divide out, and I'm left just with x. On the right side, I have negative a half times a half, so I get negative a fourth. Our second type dealing with exponentials is when they don't have a common base. And we said in our steps that our first task is to isolate the base with the variable. So in this first equation, 4 to the x is kind of done for us. And then we're going to take the natural log of both sides. Okay, and then what that allows us to do is take advantage of that ln property where I can bring the exponent out front as a product. Oops, don't want to switch to a different base here. That'd be really sad. Okay, and then I want to, so I'm trying to solve for x, so we'll just divide both sides by the ln of 4. And so I get x is the ln of 15 over the ln, doing it again, of 4. And that's actually a perfectly fine exact answer. And if the directions ask you to give a decimal approximation for that, then clearly you would pull out your calculator and just like change a base, you would type that in. Next example, we get 9 to the negative x equals 2. So I'm going to take the ln of both sides. So that brings that exponent out front of negative x ln of 9 equals ln of 2. And I apologize, I just caught that I did not write ln in front of the 2, where I should have done that because I took the ln of both sides. All right, now from here, you know, think about it, what's our goal? Our goal is to get x by itself, right? So what do I have to divide by? Well, I got a negative and I got an ln of 9, so I'm going to do divide by a negative ln of 9. All right, so then we get x is negative ln 2 over ln 9. Remember, with negative signs, kind of clarify this. So if I have a negative a half, that's equivalent to 1 over negative 2, and that's also equivalent to a negative 1 over positive 2. Where the negative goes doesn't really matter. There's 3 different ways you can write it. Most commonly, we just stick it out front. But anyways. All right, so last example with this type, the 40 e to the 3x minus 3 equals 237. So my first task is to isolate the base with the exponent. So I need to get e by itself first. So I'm going to add 3. So that gives me 40 e to the 3x equals 240. And then I want to divide by 40. So I get e to the 3x equals, and how many times does 240 go into 40? Or 24 go into 4? That would be, I'm sorry, 4 go into 24. That would be 6 times. Then I want to take the ln of both sides. And remember that ln of e to anything, that's going to simplify down to a very pretty number. So on the left side, I get 3x. And on the right side, I still have ln of 6. And then, I'm still trying to get x by itself, so I'll divide everything by 3, and I get ln of 6 over 3. And that's actually a perfectly good answer. You cannot divide the 6 by the 3 because it's not 6, it's ln 6. And division doesn't allow us to play like that.